Hi friends, welcome to follow up. First, Happy New Year. So today is the first day of the new year, so we start with some simple problems. First, let's look at problem 455, assign cookies. This is also a daily challenge problem. So in this video, our goal is the following. First, we are going to do a simulation implementation of this problem. And secondly, we are going to practice the two-pointer trick. So in this problem, the logic is very routine. Therefore, we will look at the problem statement, then we directly go to the coding. So now let's look at the problem statement. So here we have some child with a grade factor given by the list G. And also we have cookies. Is with size G, right? This is given by the list S. So we can assign the cookie G to the child I if the SG is greater than or equal to GI, right? So our goal is to maximize the number of our content children and output the maximum number, right? So notice that we should give each child at most one cookie if possible, right? So here we have two examples. If you look at the first example, it's the G and S are already in sorted order, right? So for the first cookie, so we can assign to the first children because it has a grade factor 1. This is equal, right? Then we pop this pair in G and S respectively. Then we have one cookie left with size 1, but the two children left has grade factor at least 2, so we cannot assign cookies anymore, so the output is 1. So in the second example, so for example, we can assign the first child with a caddy of size 1, and then we can assign the second children with a caddy of size 2 or size 3, actually the same. Therefore, the return is 2. In other words, the maximum satisfied children is unique. However, the ways to assign cookies are not unique, right? So here the constraints are the following. S and G. So here G is bounded below by 1 and bounded above by a constant 3 times 10 to the power 4. Well, for the S, it can be empty, right? Because it can be length 0, and it bounded above by the same number 3 times 10 to the power 4. And so GI and SI fit a 32-bit unsigned integer, right? So with that said, we can do the coding directly. So in my first solution, I'm going to give a simulation. So here for convenience, I'm going to sort and introduce some queue or deck container. So first I want to do sort. So here we sort in place. So G sort and S sort. And then I'm going to translate or change G to be a deck. So because I want to use the pop left or method. So here deck G. Similarly for S. So it's collections deck S. So now we finished our preparation. Now we began to sign our caddy. So for this, I'm going to use the bisect module. So because we want to find the corresponding for each cookie, we want to find if we can assign to some child. So we always assign it to the child with smallest grade factor as current step. So let me first write the code, then the logic will be automatically clear. So basically, we introduce a counting variable called result. We are going to return its final state. So now we are going to write our while loop, while G and S, right? Then what we are going to do? So first, I'm going to search the IDs. So here, I'm going to use the bisect module. So bisect right. So we are going to search on this G, current state, and then we are going to search for this cookie S0. So because our condition is G and S are not empty at the same time. So this S0 and G are both valid, right? So this ID, because here we are using bisect, right, means that to the left of this IDX, all the greatness is less than or equal to this S0, right? Because if it's equal, we can still assign. So this is the important point. So now we want to check if IDX equals 0, which means that so all the children actually has a larger greedy factor than this cookie. So we need to consider the other cookies in the right. So in this case, we're going to do pop left, right? So pop left from S, right? Then we continue the while loop. Otherwise, so if IDX is not 0, then it means that the leftmost, we can assign the current caddy to the leftmost children, right? So in this case, so we do a pop left. This corresponding to we assign this candy. Let's do this. As pop left, assign this candy to this child, and then we are going to increment the result counting by 1, right? So then after this, we can do the return. So this is the one solution, but this solution is very verbose. The reason is that we simulate all the process. So now, before we move forward, let me first do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So here, we did something extra. So here we translate this to be a deck, and then we do this binary search. So you can actually analyze the temp complexity. For example, for the sorting, it's a typical n logarithm n temp complexity operation. So here, basically, let's take linear or log time. So it's linear time to be precise. So here, the bisect search is logarithm operation. So this, however, because we have done this, so this pop left operations are all 1, right? So then you can add them together and do some job out, so you can get the temp complexity. So, but if you inspect this a little bit further, we don't need to do this operations in practice, because we can use pointers to mimic this situation. So now this comment actually brings us to the next solution. So for next, I'm going to copy this part. So I'm going to change this one to be version v1. So here I'm going to use two pointer trick or method. So for this, I'm going to do essentially the same thing, but we don't need this operations. We just need to move the pointers. So here first we do G sort and S sort. So this is routine, right? So now I'm going to initialize a result variable, same as above. And then we are going to start from ij equals 0. So here I'm going to use the left pointer for the G, the children greedy scores, and the G corresponding to the position of the corresponding caddies. And then we are going to use a while loop. Well, so here I'm iterating from left to right. So if I is less than length G, right? And J is less than length S, right? So in this case, we are trying to assign SG to GI if possible, right? So now we just need to check this possibility, right? So if SG is greater than or equal to GI, then we can assign the cookie G to children I. See, in this case, we just need to move I to the right, because the previous I already signed a cookie, right? So also we need to move the cookie to the right. So in this case, also we need to increment the result. This corresponding to this part, this else block. But you can also write in the corresponding to this if else block in So let's do this. Let's see. If SG is less than GI. So in this case, we just need to increment G, right? Because the current we cannot assign the current caddy to the children. So otherwise, right? Then what we are going to do is the following, right? And then this if-else block is in exact correspondence. So let's delete this condition, right? So this current if-else block is in correspondence with this if-else block. So after that, so actually we can do return. So because the logic is the same, but the only difference is the format. Let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, this actually this is the second version. But actually, if you further examine this problem, you can see it might be best to assign from the right. So now let me modify this a little bit. I'm going to copy this version. So here I would call this version v2. So here we assign from the small cookie to larger cookie, right? Smaller to larger. Then actually this is not very not the best. So in practice, we can first count the largest cookie and try to assign to the largest possible greedy children. So in this case, we are going to assign from right to left, or from large to small. So after we do the sort, actually we can let I and J point to the right. So here let's use I equals the length of J minus 1, and J equals length S minus 1. Then we want to change this condition to be, so if I is greater than -1, or you can change it to be greater than or equal to 0. And if J is greater than -1. So in this case, we do the same thing, right? If S, so in this case, we are going to decrement, right? So this will be decrement, and this will be decrement. Then the result is still, increment. This is very natural. So this also forms a solution. But, among those three solutions, so from the point of view of practice, maybe it's the first one is using some power, or just a brute force simulation. The second one is a little bit better, and the last one actually is the most proper in a sense. So now let's do a test. Let me see. IG. So length J, I is greater than if J, S is J minus 1. So in this case, let's see. We don't. If SJ is less than GI, we need to actually in this we need to use smaller greediness. That's the right one, right? Now let's do a test. So a little bit asymmetric, right? In this case. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. With that said, basically we finished explaining the solution. So essentially, the three formats of solutions are the same in logic. But our goal here, as we mentioned at the very beginning, is to do a simulation to digest the problem requirements. And then we want to actually demonstrate the use of two-pointer trick. So with that said, I guess that's about it for this video.